Welcome to Chapter 12 of the AEON-CASIMIR Dossier, where we move beyond traditional sensors and explore how the AEON LCV Omega-1 craft perceives reality itself. Unlike conventional vehicles that rely on radar, cameras, and inertial measurement units, this chapter introduces a radical shift. Sensing is no longer about collecting data from the environment, but about achieving true space-time awareness. Here, the craft doesn't just observe its surroundings, it measures the very fabric of space-time. This new paradigm is essential for navigating and controlling a vehicle operating within engineered space-time curvature, setting the stage for a deeper understanding of advanced perception. The objective of this chapter is to redefine what it means for a craft to sense its environment. Traditional vehicles use radar, optical cameras, and inertial measurement units to detect objects and navigate. However, for the AEON-CASIMIR craft, these methods are insufficient. Operating within engineered space-time curvature demands a new approach. The craft must perceive not just objects, but the underlying structure of space-time itself: curvature, vacuum stress, temporal gradients, field coherence, and mass energy distributions. This chapter lays out how the AEON LCV Omega-1 achieves this, setting a foundation for advanced navigation and safety. In classical systems, sensors detect objects within space-time. Think of a radar pinging an airplane or a camera capturing an image. AEON-CASIMIR's approach is fundamentally different. Its sensors are designed to detect the structure of space-time itself. Instead of focusing on external objects, the craft measures quantities like the metric tensor, Ricci tensor, vacuum stress energy, and field gradients. This real-time awareness is crucial for navigation, control, and safety, especially when the craft is immersed in dynamic space-time environments. The paradigm shift is clear. Perception is now about understanding the geometry of reality, not just its contents. The primary tool for this new perception is the Spacetime Gradient Sensor, or SGS. Embedded throughout the hull boundary of the AEON LCV Omega-1, these sensors measure how the space-time metric changes with position. By detecting the gradient of the metric tensor, the craft gains directional awareness of curvature, can sense external gravity wells, and receives early warnings of metric discontinuities. This capability is vital for safe and precise navigation, especially when encountering unexpected gravitational fields or space-time anomalies. SGS technology forms the backbone of the craft's advanced perception system. CASIMIR cavities within the craft serve a dual purpose. They are both actuators and highly sensitive sensors. When the boundary conditions of these cavities shift, measurable changes in CASIMIR energy occur. By monitoring these shifts, the system can detect nearby mass concentrations, vacuum anisotropies, and field interference patterns. This unique approach allows the craft to sense subtle changes in the vacuum state, providing an additional layer of environmental awareness that goes far beyond conventional sensors. CASIMIR boundary state sensing is a key innovation in the AEON-CASIMIR's perception suite. The AEON LCV Omega-1's plasma rings are more than just propulsion components. They function as distributed sensor arrays. By analyzing the oscillation modes of plasma, the system can map spatial variations in electromagnetic field gradients, charged particle flux, and the strength of vacuum plasma coupling. This process, known as plasma resonance tomography, enables the craft to construct a three-dimensional environmental field map. Such comprehensive mapping is essential for understanding the craft's immediate surroundings and for anticipating changes in the space-time environment. To accurately gauge its velocity and temporal alignment, the craft employs metric Doppler sensing and temporal drift analysis. By measuring frequency shifts due to velocity differences and comparing internal and external clocks, the system detects relativistic velocities, temporal shear, and frame misalignments. This information is crucial for maintaining synchronization with both internal systems and the external environment, ensuring the craft operates safely and efficiently even at high speeds or in regions of intense space-time curvature. A critical safety feature of the AEON-CASIMIR's perception system is inertial null verification. The craft continuously monitors whether its occupants remain in a state of freefall, meaning no felt acceleration. If any deviation is detected, the system immediately triggers metric correction, coherence adjustment, or emergency stabilization. This feedback loop is essential for occupant safety, ensuring that the craft's advanced propulsion and navigation systems do not inadvertently subject passengers to harmful forces. All sensor outputs, whether from spacetime gradient sensors, Casimir cavities, plasma arrays, electromagnetic, or optical systems, are integrated into a unified perception model. This multi-sensor fusion architecture leverages AI to resolve noise, decoherence artifacts, and conflicting measurements. By synthesizing diverse data streams, the system constructs a coherent and reliable understanding of the environment, which is vital for both autonomous operation and human oversight. One of the most remarkable features of the AEON-CASIMIR's perception system is its ability to sense beyond the line of sight. Because the craft detects space-time curvature before matter, it can sense massive objects and gravitational gradients long before they become visible. This capability enables blind navigation, obstacle avoidance without vision, and deep space situational awareness. The craft essentially feels obstacles and hazards through space-time deformation, providing a significant advantage in unknown or hazardous environments. The AEON-CASIMIR system maintains two simultaneous perceptual realities, the internal coherent frame and the external relativistic frame. Mapping between these frames is essential to prevent sensory paradoxes or disorientation. The system ensures that all sensor data is correctly interpreted, maintaining a seamless experience for both the craft's AI and its human operators. This dual-frame awareness is a sophisticated solution to the challenges posed by operating in engineered spacetime. Most of the AEON-CASIMIR's sensing is passive, non-emissive, and boundary-based. This approach avoids radar reflections, electromagnetic emissions, and other detectable signatures. By listening to spacetime rather than illuminating it, the craft maintains a high degree of stealth. This is crucial for both security and operational effectiveness, allowing the craft to operate undetected in sensitive environments. The AEON-CASIMIR sensors are finely tuned to detect subtle shifts in vacuum stress, plasma resonance, and coherence length. These measurements provide early warning of potential system failures or instabilities. By predicting failures before they develop, the craft can take corrective action, ensuring continued safety and operational integrity. This predictive capability is a testament to the sophistication of the craft's perception architecture. Sensor data is not isolated from the craft's control architecture. Instead, it directly drives metric steering, energy modulation, and coherence enforcement. This tight integration means that perception and control are inseparable. The craft's awareness of spacetime directly informs its actions. Such a feedback loop is essential for precise maneuvering and maintaining stability in complex environments. Human operators of the AEON-CASIMIR craft interact with the system through field-abstracted visualizations, curvature maps, and stability indicators. They are shielded from the raw complexity of tensor data, with AI mediating and simplifying the information. This ensures that operators can make informed decisions without being overwhelmed by the underlying mathematics, striking a balance between advanced technology and human usability. In summary, Chapter 12 establishes that the AEON-CASIMIR craft senses spacetime itself, not just objects within it. Casimir and plasma systems serve dual roles as both actuators and sensors, while curvature awareness enables navigation even without visual cues. The craft's perception is geometric, not optical, and this awareness is inseparable from control. The AEON LCV, Omega-1, doesn't look outward. It feels the very shape of reality around it, setting a new standard for advanced vehicle perception. To appreciate the leap made by AEON-CASIMIR, it's important to understand classical sensing methods. Traditional vehicles rely on radar to detect objects at a distance, optical cameras for visual input, and inertial measurement units to track motion. These systems are effective in conventional environments, but are limited when it comes to navigating engineered spacetime. The limitations of these methods highlight the need for a new approach, one that goes beyond simply observing the environment to actually measuring its underlying structure. The AEON-CASIMIR craft sensors target specific spacetime quantities: the metric tensor, $G, mu, nu, $, Ricci tensor, $R, mu, nu, $, vacuum stress energy tensor, $T, mu, nu, text, vac, $, and field gradients, nabla, phi, $. Real-time awareness of these quantities is essential for navigation, control, and safety. By focusing on these fundamental aspects of spacetime, the craft achieves a level of perception that is both deeper and more precise than anything possible with traditional sensors. With spacetime gradient sensors, the craft achieves directional curvature awareness. This means it can sense not just the presence of curvature, but its direction and magnitude. Such awareness allows the AEON LCV, Omega-1 to detect external gravity wells and anticipate changes in the spacetime environment. Early warning of metric discontinuities is especially valuable when navigating regions with unpredictable gravitational fields or spacetime anomalies. Casimir boundary state sensing relies on detecting shifts in Casimir energy. When the boundary conditions of a cavity change, the energy within that cavity also changes. By monitoring these shifts, the AEON-CASIMIR system can detect nearby mass concentrations, vacuum anisotropies, and field interference patterns. This method provides a sensitive and non-intrusive way to monitor the environment at a fundamental level. The plasma rings in the AEON LCV, Omega-1, are analyzed for their oscillation modes, which depend on local electron density and electromagnetic properties. By measuring the spatial variation in plasma frequency, the system can detect electromagnetic field gradients, charged particle flux, and the strength of vacuum plasma coupling. This information is used to build a detailed three-dimensional map of the craft's environment, enhancing both navigation and situational awareness. Metric Doppler sensing allows the craft to infer velocity and time rate differences by measuring frequency shifts. This is especially important in relativistic environments, where even small differences in velocity can have significant effects. By combining Doppler measurements with internal clock comparisons, the system can detect relativistic velocities, temporal shear, and frame misalignment, ensuring precise synchronization and safe operation. The inertial null verification loop is a safety-critical feature. By continuously checking that the felt acceleration approaches zero, the system ensures that occupants remain in freefall. Any deviation triggers immediate corrective actions, such as metric correction or emergency stabilization. This loop is vital for protecting the crew and maintaining the integrity of the craft's advanced propulsion systems. All sensor data is funneled into a unified perception model, represented mathematically as $mathcal_p teng equals text SGS text Casimir text plasma text EM text optical $. This model integrates information from multiple sources, allowing the AI to resolve noise, decoherence, and conflicting measurements. The result is a comprehensive and reliable understanding of the craft's environment, essential for both autonomous and human-guided operation. A unique aspect of the AEON-CASIMIR's perception is that it senses curvature before matter. This means that massive objects and gravitational gradients are detected before they are visible. The craft can anticipate obstacles and hazards, enabling blind navigation and deep space situational awareness. This capability is a game-changer for exploration and safety in unknown environments. Because the craft senses space-time deformation, it can avoid obstacles without relying on visual input. This is especially useful in environments where visibility is limited or non-existent. The system's ability to feel the shape of reality allows for safe and efficient navigation, even in the most challenging conditions. The AEON-CASIMIR's advanced sensors provide unparalleled situational awareness in deep space. By mapping spacetime curvature and detecting gravitational gradients, the craft can navigate safely through regions that would be hazardous or impossible for conventional vehicles. This capability is essential for long-duration missions and exploration beyond our solar system. Maintaining a mapping between the internal coherent frame and the external relativistic frame is crucial for the AEON-CASIMIR system. This mapping prevents sensory paradoxes and ensures that all sensor data is interpreted correctly. The system's ability to reconcile these two frames is a sophisticated solution to the challenges of operating in engineered spacetime. The AEON-CASIMIR sensors are designed to be passive and non-emissive, relying on boundary-based measurements. This approach minimizes radar reflections and electromagnetic emissions, making the craft difficult to detect. By listening to spacetime rather than illuminating it, the craft achieves a high degree of stealth, which is essential for sensitive missions and operational security. Unlike traditional sensors that emit signals and wait for a response, The AEON-CASIMIR's perception system listens to the subtle cues of spacetime itself. This method is not only stealthy but also provides a richer and more nuanced understanding of the environment. The craft becomes attuned to the very fabric of reality, sensing changes that would be invisible to conventional instruments. By monitoring subtle shifts in vacuum stress, plasma resonance, and coherence length, the AEON-CASIMIR system can predict failures before they occur. This predictive capability allows the craft to take corrective action, preventing instability and ensuring continued safe operation. Early detection is key to maintaining the integrity of the craft's advanced systems. Sensor data is tightly integrated with the craft's control and navigation systems. Information from the perception suite directly informs metric steering, energy modulation, and coherence enforcement. This integration ensures that the craft's actions are always based on the most accurate and up-to-date understanding of its environment, enabling precise and responsive control. Human operators interact with the AEON-CASIMIR system through field-abstracted visualizations. These displays present complex information in an intuitive and accessible format, including curvature maps and stability indicators. By abstracting away the raw tensor data, the system ensures that operators can focus on decision-making without being overwhelmed by technical details. The complexity of the AEON-CASIMIR's perception system is managed by advanced AI. The AI mediates between raw sensor data and human operators, translating complex tensor information into actionable insights. This mediation ensures that the full power of the craft's perception capabilities is accessible without requiring operators to be experts in advanced physics. A fundamental principle of the AEON-CASIMIR system is that perception always precedes control. The craft must first understand the shape and dynamics of spacetime before it can safely and effectively navigate or manipulate its environment. This principle underlies the entire architecture of the craft's sensor and control systems, ensuring that every action is informed by a deep awareness of reality. The AEON-CASIMIR's perception is fundamentally geometric, not optical. Instead of relying on light or electromagnetic signals, the craft senses the shape and curvature of spacetime itself. This geometric awareness provides a richer and more reliable understanding of the environment, especially in conditions where traditional sensors would fail. The AEON LCV, Omega-1, does not simply look outward, it feels the shape of reality around it. This approach to perception is a radical departure from traditional sensing methods, enabling the craft to operate safely and effectively in environments that would be inaccessible to conventional vehicles. By sensing the very fabric of spacetime, the craft achieves a level of awareness that is both profound and practical. This cutaway view provides an overview of the AEON-CASIMIR sensor systems. It illustrates the integration of spacetime gradient sensors, CASIMIR cavities, plasma rings, and the unified perception model. Each component plays a critical role in achieving the craft's advanced awareness and control capabilities. The image highlights the sophistication and complexity of the AEON LCV, Omega-1's perception architecture. As we reflect on the field architecture described in previous chapters, it becomes clear how essential advanced perception is to the AEON-CASIMIR's operation. The integration of sensors with field control systems enables the craft to manipulate spacetime safely and effectively. This synergy between perception and control is at the heart of the AEON LCV, Omega-1's revolutionary capabilities. Navigating within engineered spacetime requires a level of perception far beyond what is possible with traditional sensors. The AEON-CASIMIR's ability to sense curvature, gradients, and field coherence allows it to move safely through complex and dynamic environments. This capability is essential for both routine operations and exploration of unknown regions. The AEON-CASIMIR's perception system provides real-time situational awareness, allowing the craft to respond instantly to changes in its environment. Whether it's detecting a sudden gravitational anomaly or anticipating a field discontinuity, the system ensures that the craft can adapt and maintain stability. This responsiveness is a key advantage in both routine and emergency situations. For human operators, the AEON-CASIMIR's perception system transforms complex physics into actionable information. Through intuitive displays and AI mediation, operators can focus on mission objectives rather than technical details. This user-centric design ensures that advanced technology enhances rather than complicates, the operator's experience. The innovations described in Chapter 12 point toward the future of vehicle perception. As technology advances, the ability to sense and manipulate spacetime will become increasingly important for exploration, safety, and control. The AEON-CASIMIR sets a new standard, demonstrating what is possible when perception is redefined at the most fundamental level. To conclude, the AEON-CASIMIR's perception system is a leap forward in sensing technology. By focusing on spacetime awareness, integrating advanced sensors, and leveraging AI, the craft achieves a level of understanding and control that is unmatched. This chapter highlights the importance of geometric awareness, predictive safety, and seamless human-machine interaction in the future of advanced vehicles. With Chapter 12 complete, the AEON-CASIMIR Dossier moves forward, building on the foundation of advanced perception. The insights gained here will inform future developments in propulsion, control, and field architecture. As we continue to explore the frontiers of physics and engineering, the lessons of spacetime awareness will remain central to the AEON-CASIMIR initiative's mission